Hi everyone. Today my topic is classic models and deep learning method for face recognition. Let me ask a question. What is face recognition? Now we can see here are five faces from different individuals. The question is, when the sex face appears, assume that it is from the five known individuals, and then which classes it is attributed to. For human, you and me, it is a very simple question. We can recognize this face comes from the third individual in a few seconds. However, is it possible for the machine to achieve this classification? This is the main idea of face recognition. Until now, this technique has been developed for more than 60 years. There are so many different and effective methods in this field. Now, let me introduce several methods. In general, face recognition technique could be divided into two classes, the classic models and the deep learning method. The classic models have been developed for a long time and has been widely used until now. The earliest computational model is based on the features of face, such as eyes, nose, and mouth. But actually, according to information theory, these features are not sufficient enough to represent a face. Thus, the eigenface model was proposed. After the classic eigenface model, more improvements based on it were developed, such as the Bayesian face recognition and the improved joint Bayesian models. Different from the classic models, deep learning method was developed in about 2000. It could achieve more accurate results and is predominant nowadays. The convolutional neural network, also known as CNN, makes it possible to deal with the natural image data, which is once intractable with huge quantities of data. And more recently, the deep hidden identity features, also known as deep ID method, lead face recognition to a more promised future. Next, I will make a general review of these above methods, and after that, I will show you some experiment results of them. First, the classic eigenface model. Here are some main ideas of eigenface model. The key of eigenface is projecting image from face space into a subspace, and then we can calculate the similarity. The method to get the subspace is principal component analysis. Specifically, it requires finding eigenvectors of the covariance metric for training set collection. Here's the 5 steps of classification by eigenface model. Specifically, in the fourth step, due to the length of each face vector is m squared, C is an m squared by m squared metric. If we directly calculate its eigenvector, it will be very complex. Fortunately, we can use principal component analysis to simplify the operation. Here, we rewrite the equation as A transpose by A, and then find its eigenvectors. When the both sides of above equation multiplied by A, it can be written as the second formula. Thus, mu k could represent the eigenvectors of C. In the fifth step, the process of projecting face onto subspace, the weight correlation is being used. The vector omega demonstrates the contribution of each eigenface when representing each input individual face. One effective method to classify the testing face is to find the minimum Euclidean distance epsilon. When the minimum epsilon is smaller than the threshold, it could be classified into label n. Second is the classic Bayesian face recognition. Although the classic eigenface model considers about variance, it doesn't ignore the difference between variation types, since it only uses the simple Euclidean distance to achieve the classification. Assume that the variation of face images could be represented as delta equals to I1 minus I2, where I1 and I2 denotes two different images at intensity. Then we define two sets of delta. Omega I denotes the intrapersonal variation, whereas omega E denotes the expressional variation. By Bayes' rule, the posterior probability of omega I given delta could be solved as the last equation. The problem here is, when there are two classes as shown in the screen, class A is the left circle and class B is the right one. When projecting onto the x minus y line, there will be an overlap area, which is shown in red. The following joint Bayes method solves this problem by constructing a joint probability of omega I and E. To solve the problem to find the joint probability, we consider this situation. Try to imagine that face of any individual is composed by identity and interpersonal variation. Mu is used to differentiate individuals, and epsilon is the variation of the same individual with different expression. Assume that they are independent and both Gaussian distributed. Thus, an individual face could be represented as x equals to mu plus epsilon. Furthermore, we can derive the covariance metric of two face images. With this joint formula, we can get the log likelihood function as follows, where S mu and S epsilon could be found by EM algorithm. After talking about a serious classical model, let me have a look at deep learning method. Before the advanced deep ID method, I want to make a summary of deep learning and the convolutional neural network. The whole neural network in deep learning is composed by a single unit. Each unit is like this, and here is the formula of each output. Note that since a network architecture includes a great deal of parameters, it requires big data for training, otherwise it might be overfitting. In practical, when processing images, the tremendous number of parameters makes training intractable. Thus, the CNN was proposed. This algorithm could effectively reduce the number of parameters and hence simplify the structure and speed up the learning procedure. There are four keys for CNN. The first is local connection. Since the local groups of pixel values is usually high correlated in one image, it is possible for each neural unit to locally connect limited input values. The second is share rate. Actually, most parts of one image usually share the same local statistics, which means the learned features of one part could be used for another. Thus, the weights which represent the features could be shared for different local patches. The third is the design for multi-filter. Since the single unit is connected with reduced local patches, now the feature extraction might be insufficient. To avoid this situation, multi-filter bank could be used to generate different layers. The last key idea is down pooling. Since nature image is stationary, thus, we could merge semantically similar features into one, and this operation is called pooling. Now, let me talk about the recently deep ID method. There are two ideas about deep ID. The first is partition. It means partitioning one face image into several patches and training the features for these patches separately to get trained features weight. Finally, these independently extracted features from various local patches are connected to form complementary and over-complete representations. The second is connection. The structure of deep ID method is similar to convolutional net. The difference is, before the softmax layer, a deep hidden identity layer is found by directly connecting the last convolutional layers and the max pooling layers. After the first DeepID model, the improved DeepID2 was then developed. In this one, a joint identification, verification, and supervision is added. Generally, the identification and verification function are represented like this. Note that since the verification function requires two samples, Fi and Fj, thus there is an adjustment of the training per set. In DeepID, an individual face image is divided into several patches to be trained, while in DeepID2, two samples are randomly selected in each iteration and training. Now, let me show you some experiment results. First is the eigen face experiment. In the simulation work, we use 400 face image of 40 different individuals to achieve the classification. The algorithm first randomly selected images of each face as training set and then randomly select 500 images from the whole data set as the testing set. For different values, we took 500 independent trials and the average accuracy of classification is recorded in this table. It can be easily seen that when increasing M, which means increasing the training samples for each individual, the accuracy will be improved. Then is the Bayesian model. For the intrapersonal and extrapersonal set, we took totally 800 pairs, 400 in each set. This feature illustrates the comparison between classic eigenface model and the classic Bayesian model. Obviously, Bayesian face can perform obviously better than eigenface model under low-rank condition. Then for joint Bayesian, still 800 pairs are used for classification, and we set the threshold as theta equals to minus 8.73. In each trial, two face images were input. If the outcomes bigger than the threshold, then two faces are considered as from the same individual, otherwise from different individuals. This table illustrates the outcomes of 100 independent trials. Finally is the experiment of the first DeepID model. The train error and valid error after each iteration is recorded. The figure illustrated after approximately 10 iterations, both train and valid error are converged to less than 0.1. Moreover, when we choose the deep hidden identification layer, we could directly use this features data to classify face and make comparison with the face recognition based on PCA technique. The comparison of two methods above is listed in this table. It can be easily seen that the DeepID model could achieve more accurate results. Finally, I want to make a conclusion of this topic. For class method, some key ideas are still widely used and is based for many improved methods nowadays. As for deep learning method, it could achieve better results than classic method, especially when dealing with large quantities of data. Moreover, when the structure is improved, for example, the architecture should be adapted to the size of data and some metric learning techniques could be introduced in the architecture. Then the performance of face recognition could be improved. Thank you for your listening.